do a couple of examples real quick, and you guys can tell me what type of forces are available to these particular chemicals. So I'm going to put out some chemicals here. I'm just going to put up a list, and you guys tell me what are the forces available to these guys. We have pH3, we have CHF3, we've got CH3OH, we've got H2S, we've got O3, we've got CH3NH2. So let's just take a look at the forces available for these guys, and you guys can tell me what you think. The forces are going to be dipole-dipole, London dispersion force, and hydrogen bonding. Okay. First of all, let's identify these chemicals as to whether or not. Let me add one more in here. Forgot. Let me put in Br2. First thing you want to do an exercise like this is determine whether the chemical is polar or non-polar. That's the first thing you want to do. Okay? pH3, very similar to NH3. Is it polar or non-polar? Polar. So I'm going to put P for polar here. Okay? CHF3. It's basically tetrahedral, but one of the atoms happens to be hydrogen instead of fluorine. Polar or non-polar? Polar, because it's not symmetric. This is polar. Methanol, instead of it's got hydrogen and it's got an OH in one of the sites. Polar, non-polar? Polar. H2S, similar to water, it's bent. Okay, you guys said polar. Ozone. Looks like this, it's bent. It's also polar. Very small in terms of polarity, but it's still polar. That's why I have to put a different example, because all my chemicals are polar. This chemical right here, with NH2 at the end, that would be polar. And then finally, Br2, polar or non-polar? Non-polar. So, right away, because this is the only non-polar chemical, the only force available for Br2 is what? London dispersion force. That's the only thing you can check. That's the only thing you can check for Br2. Okay? Then the other thing you can do right away is, because all of these are chemicals and all of these have electrons, you want to check all of them. All of them will have London dispersion force. But for Br2, that's the only force you can check. Okay? We just said all of these were polar, so we can also check these off, right? Because as long as they're polar, they will have dipole-dipole intermolecular force. Now we figure out hydrogen bonding. Remember, hydrogen bonding has to do with hydrogen bonded to an electronegative element. It has to be directly bonded to an electronegative element. Is hydrogen here bonded to an electronegative element? No. So it doesn't have hydrogen bonding. How about the hydrogen here? Is that bonded to an electronegative element? No. Even though there's an electronegative element present, the hydrogen is not bonded to the fluorine. It's bonded to the carbon. So because it's bonded to the carbon, you don't have hydrogen bonding. It has to be bonded to the electronegative element, because it causes the electronegative element steals those electrons away. The carbon's not going to do that. Only an electronegative element will do that. So this will not have hydrogen bonding. How about this chemical right here, methanol? Yes, because the oxygen is bonded to the hydrogen. So we want to check that mark. Check that off. How about H2S? No, sulfur is not electronegative, so we don't want to click on that. How about O3? No, it's got no hydrogen. That's an easy one. How about CH3NH2? Yes, it does, because the NH2 means that the hydrogen is bonded to a nitrogen. That has hydrogen bonding. And finally, Dr2. No. So that's how you would do a problem like this. The first thing, like I said, you want to determine whether it's polar or non-polar. Once you do that, you can check these two off. And then to figure out hydrogen bonding, you want to look for hydrogen bonding to an electronegative element. What exactly is this experiment about? You guys are going to be, this is a pretty fast experiment. The experiment itself mostly is going to be answering those questions. But you guys have 3 chemicals that you guys are going to be analyzing. Okay? The 3 chemicals that you guys are going to be analyzing are isopropyl alcohol, glycerol, and water. Let me show you those structures so that you can see what type of chemicals you're dealing with. It looks like this. It's got a hydrogen, an oxygen, a hydrogen. There's a bond angle in there at about 108 degrees, and it's got 2 lone pairs of electrons right there. That's water. Isopropyl alcohol has 3 carbons. And I will also have the molecular model, so these things. It has 3 carbons, and the center carbon has an OH group on it. Okay? And then the other carbons have hydrogens attached. So this is isopropyl alcohol. It's got 3 carbons, 8 hydrogens, and 1 oxygen. It's got 3 carbons as well. 1, 2, 3. Each carbon has 4 bonds. This has 3 so far. The 4th bond is an OH group. This has 3 so far. The 4th bond is an OH group. And this has 3 so far, and the 4th bond is an OH group. So that's glycerol. Okay? Is water's in here. What you want to do is probably look at the clock and get the same person to do this. Swirl it and try and do it with the same energy or enthusiasm for all 3, and then stop and then time it and see how long that vortex lasts. Okay? And then when it sort of stops, then you can give it that number. This is glycerol. You want to swirl it, and then with the same vigor as the other, and then you didn't do anything. Okay? You want to swirl it, and then still didn't do anything. So again, you can do it based on that. And then isopropyl alcohol, you swirl it, and then start the clock, and then again measure the time in which the vortex lasts. So that's your first step. Pretty easy. Okay? The second step is easier. You take wax paper. Okay? Wax paper, like a well-polished car, repels water or repels certain chemical. And so what you want to do is you want to take one of the liquid, actually it has a dropper right here, take a wax paper, put it at a surface that you can see at eye level, and then add 1 drop of each liquid right on the wax paper, and then record the shape of that drop. Is it spherical? Is it flat? Because surface tension is a property that measures intermolecular force. Whenever a liquid takes on a spherical shape, it maximizes surface tension. So the more spherical that drop is, the stronger the intermolecular force. The more flat it is, the weaker the intermolecular force. So when you put a drop of liquid on that wax paper and you make your observation, look at how spherical that particular drop is. Hopefully the wax paper is going to repel that liquid, because if it's attracted to it, it's going to be flat anyway. But it's opposite from what these chemicals are. Okay? Your third procedure for this particular experiment deals with, let's see, where am I? This will take someone who's going to be a future surgeon. Okay? Maybe some of you will be surgeons in the future. You're going to take a piece of paper clip, and you're going to take probably a petri dish full of that liquid, and then you're going to slowly lower that paper clip right on the surface of that liquid and see if it floats. Because if it can float, you know that a paper clip has a higher density than the liquid. It should sink. But why would it support that particular material that has a higher density? Because of surface tension. The surface tension will hold that particular object, even though it has a higher density, and keep it afloat. But if it has a weak surface tension, then the fact that that paper clip has a higher density will cause it to sink. So if you can get it to float in one of these liquids, then you can say that that particular liquid has a high surface tension versus another liquid. Okay? So that's the third procedure. The fourth procedure will require you to take a beaker and add pepper to it. When you add pepper, pepper will float, okay? And it will be scattered throughout that particular liquid. Now you want to take a drop of soap. Soap is a chemical that will cause the liquid to recoil, because it's going to be opposite from the liquid. Okay, it's not going to be attracted to it. And so when you add it to the surface of a liquid, depending on the surface tension and the intermolecular force, the faster it recoils back. It has to do with the surface tension as well as the attractive force for that particular soap. And so you want to make your observation on that and then draw a conclusion as far as the surface tension for that particular liquid. You want to sprinkle some pepper on that surface, and you want to add a drop of soap, or even take a your glass stirring rod, put it in some soap, and just touch the surface and see how much it recoils, whether it's pretty fast or pretty weak. The last experiment that you guys are going to be doing is you're going to take, this is hard because you've got to take a container like this and fill it all the way to the top so that the liquid is just bulging but hasn't spilled over. It hasn't spilled over, okay? It's bulging right at the top. And then you want to take pennies, and you want to add pennies to the container. And if 1 penny will cause this to spill over, then again, it'll tell you something about the intermolecular forces. Some of these setup, some of these liquid might have 3 or 4 more pennies before it spills over. Okay? Again, that'll give you some information about the intermolecular force. So those are the 5 procedures that you guys are going to be doing in this lab. It's pretty straightforward, pretty easy. Make sure you rotate through the different station, and then when you record your observations, you want to draw a conclusion as to whether liquid A has stronger surface tension than liquid C, or liquid A has stronger intermolecular force than liquid B. You just want to draw a conclusion based on your observations.